Welcome back, class. It's good to be with you. This is chapter 4.2 of Militino, Ugarte, Militino, and Arnholt. And I'm very excited about this section. We're not going to go through the book in general, but I have some notes that I want to just overlay on top of the book. And the purpose of this is to just get a big picture view of what in the world these random variables are. They are, in my view, sort of the essence of the probability theory. If you can get these, you've got the key tools for working around with probability. Outside of counting. Counting is kind of understood in that. Okay, so let's get into it here. We're going to look at 7 discrete random variables. Okay? Now, the notation we'll use will typically be x as the random variable, and we'll use this little tilde, which means follows such and such distribution, and we'll have the name. Then in parentheses will be one or more parameters of that random variable. What a parameter is will make sense once we get into it. Okay, so the first one here is the discrete uniform. This is the intuitive distribution for a die. Okay, I'm not going to do it on R. I'm just going for very, very simple here. 1, 2, 3, 4, 5, 6. There's a probability of 1/6 or 1/6 of getting any one of these 6 faces on the die. And if you were to map it or graph it, this is what that probability distribution looks like. Of course, this is the PDF, sometimes written as the PMF. Okay, the CDF, you're going to add the bars together. Okay, that's it. This happens in a lot of cases. The basic format that I have in these notes is definition and then support. The support, as we saw before, when you have a random variable, then there's some sample space from which we're obtaining it. That's the domain of the random variable. And then you're mapping it into some set of real numbers. This becomes the support, the reals, and we have a probability function which maps the values of that support onto the interval 0 to 1, probability. And so the support then is the set of possible values that the random variable can take on, which I've used that term before. The technical word is support. So that's the support. Okay, in our case, it's 1 through 6. In a more general setting, let's say we have a raffle of 100 tickets, then you'll have 1 through 100. Okay, of drawing a particular ticket, let's say. All right, so I'm going to write out any assumptions, and then PMF and CDF. Okay, again, in my notes I've got PMF. In the book he's going to use PDF. Same thing. Okay, 1 over n. In our case it's 1/6, uniform throughout. Then next I have a section called key moments. Now, we have the expected value and the variance and the moment generating function stated here. I'm not going to take the time to derive them in these notes, and most of the derivations are not inside our book. So we'll be doing that some in class and some as exercises. Okay, but for now, it's intuitive, n plus 1. If our n equals 6, we have 7 over 2, which is 3.5, right? That hits us dead center right there. That's a nice expected value. Makes a lot of sense. The variance, n squared minus 1 over 12. Very interesting. We'll derive it. Applications, I put raffles, lotteries, gambling, any names drawn from a hat, that kind of situation where it's the same probability of each event occurring. Okay, number 2 is the Bernoulli random variable. The parameter for that variable is pi, okay, and it's just a single trial that has 2 outcomes. The simplest model of this is a toss of a coin. Okay? Every single toss has the same probability of success, same probability of failure. Okay, and so that's what the support is: success, fail. Sometimes that'll be written as 0, 1, and it doesn't matter which one's the 0, which one's the 1. Okay, so a lot of times we'll write success with 1, so let's just put that. Okay, now we're assuming there's a single trial, there's only 2 possible outcomes, and we know the probability of success. So probability of success, which you could say that's the probability that x equals success, or using success equals 1, let's put it here, that is pi. All right. Now, the PMF for that is worth looking at. It's pi to the x times 1 minus pi to the n minus x. That looks weird. Okay, and I put n minus x, didn't I? You know, really we should have a 1 right there. Let's just do that. Let's put 1. Okay, and that'll simplify life. Okay, so it basically works like this. The probability that x equals 1 is pi to the 1. Bing! We hit the success. And the fail, which is 1 minus pi, is 1 minus 1, because x is 1. That goes to a 0, and so we get pi. So indeed, probability x equals 1 is pi. On the other hand, if x equals 0, then I'm at pi to the x, but x is 0, so that goes away, and 1 minus pi is going to be 1 minus 0, so bing, that's in 1 minus pi. And indeed, it's 1 minus pi, so we're set. What's the expected value? It's going to turn out to be pi. I'm not going to prove it right now. It's very simple to do, good exercise. And then we've got a variance, pi 1 minus p. I have a p right there. That should also be pi. Pi 1 minus pi. Typo. Okay. Bernoulli, okay, applications. It's not so much that this is a hot item, but it's a fundamental concept that's going to be used as a building block for some upcoming random variables. Okay, so let's go on to the binomial. Okay, now binomial, x is the number of successes in n independent identically distributed trials. Okay, now we're starting to get somewhere interesting. The support is 0 through n. Okay, those are all the possible values. And let's just jump right into an example before we continue, just to hit it here. Okay, the scripts we'll be using on R are in this file here, s.331probability.r. And we'll start off with the binomial example. And in this example, I'm going to have 20 Bernoulli trials. So we put n equals 20. And each trial is a single multiple choice question with 5 possible answers. We're going to guess on each one. So when I guess, I have a 1 in 5 chance of getting it right. If I get it right, that's a success, a 1, we count it. If I get it wrong, that's a fail, and we don't count it. Okay? The probability of getting one item right is 20%, and I have 20 of them. So x is the number correct on the 20 multiple choice items. This follows a binomial probability distribution for the reasons that we'll see a little bit later. I have 20 independent, identically distributed Bernoulli trials, all with the same probability of success, namely 1/5. Okay, so the support is 0 to 20, and this line right here is going to calculate the binomial probabilities. We, of course, will derive the formula and show how to do it by hand, but I want to just get those. So we'll look at how that works a little later. Let's go ahead and just look at the PMF, okay, or PDF. There it is. We can imagine that 20% of 20 is 4, so we would expect that we're most likely to get 4 of them right. That will be the expected value. It's also the most likely of these events. But we could get 0, we could get all the way up to 8, 9. 20 is possible, it's just such a small probability that it doesn't register here. Okay, now the CDF will go ahead and show that as well. Looks like this. Notice the axis here, we actually go up to 80% on the label. It goes up to 1. And that occurs, I'm just adding each of these bars. When you add 0 and 1, boom, that's this guy. When you add it with the 2, that's this guy. And you successfully add, so this thing is monotonically increasing. All right, now let's take a look at the details then. All right, so for a binomial, we have n trials. In our case, we had 20. IID means independent and identically distributed. Basically, it means that they're all the same Bernoulli trial. Each question, we're guessing, it's the same 1/5 chance of occurring. All right, now the probability mass function. I'm not going to go into a detailed derivation. Please ask in class if you don't quite grasp this. But it basically works like this. For the Bernoulli, this notation captured, this was the success, this was the fail. So for the binomial, I have x successes. So probability that x equals x. X p's are all going to get multiplied together. And the rest are fails. So that's n minus x. For example, if x was 4, what's the probability we get 4 right? I'd have 4 successes, and then I'd have 16 fails. And so those all have to be lined up when I compute the probability, because I have success, fail, 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 success, fail, fail, success. 20 different probability calculations, but they could all be rearranged. The order is going to make a difference. Well, each different ordering counts, but I don't care what order they come in. I want to just group them all together. So we're going to use a combination, and that will add up all of the ones with this particular combination, and that gives us the probability. So this is the PMF. Okay, so that's what we got. Now, the moments, we can use this PMF to obtain the expected value and the variance, as well as the moment generating function. This thing is so useful. It's got lots and lots of applications. Polls, this is the basic way they work. When people vote, they either vote yay for this person or nay. All right, boom, so we've got a poll. Even if there's, let's say, 5 people on the list, then how many favor candidate A? Okay, well, there's a proportion who favor candidate A, and then there's a proportion who don't. So you can always break things into binomial cases. Either it is that or it isn't, even if there's more than 2 possible cases. That's what makes it so versatile. Industrial processes, they either pass or not. Sports, you got the kill or not, and so on. Okay, so that covers the binomial. Very general, very nice. Now, geometric. The geometric is kind of like the binomial in that it builds up with Bernoulli's, but the geometric is the number of Bernoulli trials that result in failure before the first success. So the geometric is like how many times do you get a shot until boom, we get the jackpot. Okay, you might think of playing a slot machine. If there's a certain percentage chance of getting the jackpot, and it's the same every time, so each time you pull that lever, then you're trying. The random variable is how many times do you have to pull that lever before the next one goes jackpot. That's geometric. Okay, so the support is 0 up through, there's no fixed endpoint on it. So that's interesting. It's potentially infinite. Of course, it is finite. There's some number in a particular application. And we basically assume that it's unbounded and all these trials are Bernoulli's. Okay, now when we do that, then the probability mass function is developed kind of like the binomial. We have X failures, so that's all the failures, and they all have to occur in a row. So there's no counting, there's no rearranging, and we have to add up all the different rearrangements. That's it. They're all fails in a row, and then boom, we've got the success. So that goes on the end. All right, we have our moments. We've discussed applications, so let's take a look at one on R here. We get the geometric application, and I've got a loib is a stock that has a nice steady rate of return, really good to have in your portfolio, except there's a certain percentage chance that if a bad news about the stock hits the market, then boom, stock drops in half once that news gets out. Okay, so we'll just suppose it's a 1% chance that the bad news occurs, and we'll look at the first 150 days and see what the probability that you have that many days before the bad news occurs. Okay, so we're going to look at 0 through n minus 1. And again, let's look at the PMF first. Oh, better pop that on there. Geometric PMF. So, let's see. We can see that. Oh, I didn't change my. That's okay. We're keeping it with n equals 20. It starts off at about 20% that we don't hit it on the first day, and then it starts going down until they're very small probabilities. Now let's look at the CDF, and you can see it's going up as we go. And always this is how it works. We're up here at 80%, and it will go higher as the days start clicking off. All right, that's what the shape looks like, and that's generally what the geometric shapes always look like. It looks like an exponential. Okay, next one. It's called the negative binomial. Now, the negative binomial is interesting because it takes the geometric and it adds one more feature to it. It says, okay, in the stock market example, we don't drop in half on the first bad news. We're going to have our pieces of bad news until we drop. Okay, so the negative binomial then is the number of failures prior to the rth success instead of just the first success. So the geometric is a subcase of the negative binomial. The negative binomial then has two parameters, whereas the geometric had only one, just the Bernoulli trial pi. So now we have to have how many successes until we count it. Okay, so the support then has to start with R, because we have to have the rth success. So that would be 0 fails, R successes. The assumptions are the same as in the geometric. The PMF is just like the geometric. We're going to have X failures, but now we're going to have R successes instead of just 1. But when we do that, we can now shuffle around R minus 1 successes. So you have to have your last one out here at pi. But now we've got 1 minus pi. We get a bunch of fails. 1 minus pi. But we get to shuffle around R minus 1 successes. So there's R minus 1 success. And of course there's X fails. Okay, so that covers both of these. And so now, how many ways are there to rearrange those guys? Well, there's R minus 1 of the successes, and we need to select those R minus 1 slots out of the total number of slots, which is X plus R, except there's 1 missing for the front position, so we'd subtract 1 here. And indeed, this can be determined to sum to 1 over X equals R through infinity. Okay, and we can obtain the moments. And the applications are similar to the geometric applications. They're a little bit richer. I've written a few of them down here. If you're in a sampling situation, we have number of butterflies counted until we get a fixed number of a certain kind. You could think of the cereal boxes. How many cereal boxes do we have to go through until we get all 5 of the special toys? If in a Happy Meal, they're not featuring the toy by month, but we have 6 special toys, so come and get your Happy Meal and get your toy. Then how many Happy Meals do you have to buy before you get all 6 of them? Okay, that's the kind of application that we have. And so moving into the R, we're going to have the same scenario as before, except instead of as the geometric case, but our stock is going to go down when we get 2 pieces of bad news instead of just 1. So same probability of the bad news breaking, 0.01, and let's see, I've got n equals 150. Let's just drop that down to 20 like we had before. That was kind of nice. And so we'll take a look at the PDF and the CDF together. Okay, steadily going up here. We better look at a larger number. Let's try 100. Look at it over 100 days. Okay, yeah, that's looking more interesting. Look at 150 days. Okay, there's a peak here around 100, as we might expect. We'd expect to tank about there. Why? Since the probability is 0.01. Should be somewhere around there. Okay, then the probabilities go down. CDF still going up. Each probability is very, very small. There's some small probability on individual day. Okay,